look a little bit more closely at 4 counting problems that have to do with order mattering and with or without replacement. All right, so again, in this video, we're talking about indistinct objects. So we have indistinct objects, and we'll say take an R at a time. So consider these 4 problems. First one, a club consists of 26 members, so people are distinct, and they a club consisting of 26 members needs to select an executive board consisting of a president, a vice president, a secretary, and a treasurer. So here, N is equal to 26. Those are my distinct members. And I'm taking them 4 at a time. I'm looking for groups of size 4. So my R is equal to 4. And I have further put, they're not just in a group, they have been assigned a role. And because of that, that is telling us that order matters. Since we're using them up, these people up, and no individual can hold more than one office, that's telling us that repetition is not allowed or without replacement. All right, so we know that this right here is a permutation of 26 items taken 4 at a time. So 26P4 or 26 factorial over 26 minus 4 factorial. All right, so we've seen that already. A club consisting of 26 members, again, those are our distinct objects, needs to select a delegation of 4 distinct members to attend a convention. So here we're looking at a group of them. We're not assigning them a role. So this is just, so again, R is equal to 4. Here, order doesn't matter since it's just a group of 4 and without replacement. So that's the distinct part right there. So this is a combination of 26 items, 26 choose 4, or 26 factorial over 26 minus 4 factorial, 4 factorial. This third one, a club consisting of 26 members, requires volunteers to complete 4 distinct chores. So again, my R is equal to 4, and I've distinguished them from each other. One chore is different than the other. Sweeping is different than dishes. N is still equal to 26. The same person can volunteer for more than one job, and each job only requires 1 volunteer. So this is telling us that order matters because the jobs are distinct, and since I can repeat one of my distinct objects, I'm saying that a repetition is allowed or with replacement. So this is for every job I have 26 choices, or 26 times 26 times 26 times 26, or 26 to the 4th. All right, this last one we haven't dealt with yet. A club consisting of 26 members requires volunteers to make 4 identical recruiting calls. A member can volunteer for 1, 2, 3, or all 4. So here again, N is equal to 26, R is equal to 4. We have distinct objects taken 4 at a time. Now, we're just looking at groups of 4. They're not we don't want to distinguish amongst our different calls. That's the identical part. And a volunteer, so that's telling us that order doesn't matter. And a member can volunteer for 1, 2, 3, or all 4, and that tells us that repetition is allowed or with replacement. And that's one that we haven't quite dealt with yet. So let's fill in our chart right here in general. So indistinct objects taken R at a time. If order matters and I'm not allowed to replace, that's NPR, or N factorial over N minus R factorial. If order matters and I'm allowed to repeat, that is N to the R. If order doesn't matter and I don't replace, that's a combination, or N factorial over N minus R factorial, R factorial. So this is the last one. So we're going to come over here and we're going to examine it. We're going to reframe it and see if we can help answer that question. All right, so when we have these indistinct objects, and I'm going to move away from 26 here, and let's say N is equal to 5 here. I'm going to translate that into 5 distinct bins. like little holders. And I'm going to use dividers to distinguish one bin from the next. So they're distinct, so I'm going to order them in that sense. So we'll say the first bin is here. That's the second bin, third, fourth, and then fifth on the end. So notice I need 4 bars to create 5 distinct bins. I know you're in a bin if you're to the left of, I know you're in the first bin if you're to the left of the first bar. If you're to the right of the first bar, I know you're in the second bin. And if you're to the right of the fourth bar, I know you're in the fifth, and so forth. Okay, so our R, so here, let's say R is equal to, I'm going to say just for fun, R is equal to 4 here. And these are indistinguishable. Which means our order does not matter. Order, no matter. And since repetition is allowed, that's meaning I get to use my distinct objects more than once, or I can place more than one object inside a particular bin. So let's say they're indistinguishable, so we'll say that they just look like this. So four balls, we'll call them 4 indistinguishable balls. And we can place them in different ways inside of our bins. So maybe I put 1 here, 2 there, none there, 1 there. That's just one way I can place. So what this means is I have 1 ball in the first bin, 2 in the second, none in the third, 1 in the fourth, none in the fifth. And I can move around these circles and these bars. So let's rewrite this above like this. 0, 1, 0, 0, 1, 1, 0, 1. So if you saw a string of zeros and ones like this tells you 1 zeros in the first bin, 2 zeros in the second bin, none in the third, 1 in the fourth, none in the fifth. Okay, and so we realize that this question of distinct objects, which we can repeat, are at a time where the order doesn't matter, can be translated into a string of zeros and ones. And so this should remind you of that Texas problem where we had repeated E's and A's. And so really I just have, in this case, I have 4 balls plus 4 dividers. So I have 8 letters, if you will. And 4 of them repeat, 4 of the blue ones repeat, and 4 of the green ones repeat. So remember how we did this. So we take all the arrangements of these 8 objects, 8 factorial, and then we divide out the ordering of them within their particular place. And what I mean by that is I don't want to count this 0 moving to that 0 and all the ordering, all the arrangements of those zeros in those particular bins. So we divide out 4 factorial, and then the same with our bars. Divide out 4 factorial. Okay, so let's go back to this question here. A club consisting of 26 members, N is 26. So we have, how many bins do we have? We would have 25 bins. Remember, we only need 1 less divider for the number of bins. And they're identical calls, so we have 4 balls that are indistinguishable. Okay, so we have a bunch of bins, well, dividers that denote the bins, and then we have these 4 balls. So we really have 25 of them. I'm just not writing them here. So we look at all the arrangements of those, which is 25 plus 4, and then we divide out the repeated ones. So those 25 dividers, they look identical, and those 4 balls look identical. So let's do it in general. Well, we have indistinct bins, which means we have n minus 1 bars. right? Our n minus 1 dividers. And we have our indistinguishable balls, so plus r. We take the n minus 1 plus r factorial, that's what we did up here. And then we divide out the identical bars, which is n minus 1 factorial, and the identical balls, r factorial. Let's look at one more example together. Let's look at this one. Rick wishes to select a dozen bagels from Murray's. Her choice includes Asiago, plain, wheat, cinnamon, and salt. So these are my distinct objects. I have, how many is that? 5. N is equal to 5. So if I wanted to create dividers to 4, right? So this slot right here represents Asiago, plain, wheat, cinnamon, salt. All right. He wants to get a dozen bagels. So the bagels themselves, like if I got 2 Asiagos, we're saying that that's indistinguishable. So in other words, if I had 2 here, I don't want to account for also the flipping of those 2, right? I don't want that to be a separate thing. So they go in there. We don't care about the order once they're in the bin. All right, so how many ways can she order a dozen bagels if we have the 5 different types? So again, we would say n minus 1 plus r factorial over n minus 1 factorial, right? Because these bars are indistinguishable and the 12 balls are indistinguishable. Divided by 12 oops, sorry, that should say r factorial at this point. And then we'll write it. Or 5 minus 1 plus 12 factorial over 5 minus 1 factorial and 12 factorial. Let's look at this one. How many different orders of a dozen bagels can she select in which she has at least one of each kind? Well, it might sound hard, but what it really just means is of the 12, we already know exactly where 5 of them go, right? So instead, we now have r is equal to 7 because we already know there's a ball in there. They're not going to move. So really the question becomes, how many different ways can 7 balls be placed into these 5 distinct bins where repetition is allowed? So we still only have 5 here, so we would have 5 minus 1 plus 7 divided by 5 minus 1 factorial, 7 factorial. That's it.